Now let us now try to calculate the range equation for FSO link. This is my Tx. So how do I design a system? Suppose I want to design a system, say for example, 5 kilometer, and I want to design a system for say 3 gigabits per second, and my quality of service or the reliability or the probability of error, say for example, of this order. So how do we design what should be the level of the transmit power, what kind of source I should use, a laser source, and what kind of divergence angle, what kind of receiver, what kind of antenna gain at the transmitter, antenna gain at the receiver, right? When these parameters are given. Or there can be a system which has thousands of kilometers, for example, space links, geosatellite, from one geosatellite to another geosatellite. Then what kind of components I need, or what kind of antenna gain and the transmit receiver I require. So we'll try to understand this using range equation for free space optics link. So the idea is to how much photons I detect at the signal, and how much are the background noise photons. It can come from solar radiations, it can come from noise of the receiver. So basically this gives me the signal part, and this will give me the noise part. So this also includes detector noise. So this is how because for meeting this requirement, I need some signal to noise ratio at the receiver, or some receive power, which will satisfy this requirement of 5 kilometer, 3 gigabits per second, and beta rate of 10 raised to -9. So let us now build the theory part first, and then we will understand this using two examples. So free space loss is generally given by Ls is equal to lambda by 4 pi r whole square, where r is the link range. This is r, for example. So this is the free space loss, lambda by 4 pi r whole square. Now let us see that this is the transmit power, which can be written in this form, where B is actually your brightness, or we can use another term which is luminance. And the luminance is actually given as candela per meter square, where candela is your lumens per solid angle. So the units are actually lumen. For solid angle, it is steradian into area. So this B is brightness or luminance, which is actually candela per meter square, and candela we know is lumen per steradian. So this is, you can see here as well, B is brightness, which is luminance, into the area, into the solid angle. So PT AS omega S is the transmit power. Now let us assume a Lambertian source. Lambertian source is basically, it is emitting like this, and this varies as intensity here will be, say for example, I0, and this angle is theta, so this will be I0 cos of theta. So if I convert this angle, this whole angle, let us call it as a theta s, to solid angle. because ultimately the power is going in the solid angle. So there's a converting into this angle into a solid angle, we can use this formula 2 pi 1 minus cos of theta s divided by 2. So this theta s, actually the limits are, minus pi by 2 to pi by 2. So the total angle is actually pi. Lambert source can emit anywhere in this range. So the maximum limit of theta s is pi. So if I put this theta s pi here, I get this solid angle as 2 pi, which I have used here, and I have put this omega s as 2 pi. So my PT becomes 2 pi into luminous function into the area. So now let us understand near and far field of light emission using beamforming optics. Because I'm using telescope or lens arrangement in the transmitter and the receiver. So let us understand the concept of near and far field of light emission using beamforming optics. So for example, this is your laser source. And you have beamforming lens here or optics here. So the beam from the laser source will come, gets converged, and then starts diverging. This is what happens. So let us define this as midpoint. So let us define different angles here. This is, for example, your theta s, this small angle, the divergence, let us call it theta s. And the transmit aperture is, let us call it dt. And similarly, you have the receive aperture at distance r. So this is a range, for example. So this will be, let us call it as a dr, or the planar beam diameter, or the receive aperture. So dt and dr, they are defined, and then let us call it as a beam angle as this, and let us call this as a theta b. So theta b is the beam angle, and this is using this lens I am able to beamform. But as it travels in the environment, it diverges, and this is defined by this dr, which is a planar beam diameter. So this dr, which is the receive beam diameter, is actually given by dt plus theta s. Theta s is the divergence angle into the r. So as r increases, this quantity will increase and gets added up, and then there is an expression which is dr is equal to dt plus theta sr. Now I am squaring these terms, dr square into dt square. I have taken dt square common, so this becomes 1 plus theta sr divided by dt whole square. Let us take this dt whole square here. So this becomes, expand this becomes 1 plus theta sr divided by deta t whole square plus twice of theta sr or dt. Now I am using that theta s, the divergence angle is actually lambda with dt. To be precise, it is 1.22 lambda with dt, but let us not worry about that 1.22 factor. We can take this as 1. So theta s is approximately lambda with dt. So putting these values here, lambda by dt, I get this. Now, when your r is small, that is a near field. So this quantity and this quantity is actually less than 1. Then dr square dt square is equal to 1, then dr is equal to dt. So this is the near field equation here. So basically this quantity lambda r by dt square is less than 1. So you have dr is equal to dt. The far field, you cannot neglect this term. And the second term is actually square, and the third term is actually, under root of this. So basically it will be dominated by this second term here. So this equation will be dr is equal to lambda r by dt when under this condition, when lambda r is equal to dt square is greater than 1. So this is far field. So let us write here. So dr is equal to dt when you have near field, and dr is equal to lambda r divided by dt when you have far field. The theta b, the beam angle actually is given by dr by r. This you can see from here, because if you take, 10 theta by 2, I take half the angle theta by 2 here, this angle for example, theta by 2 is actually can be written as dr by 2 divided by r. And this angle is generally small, so this can be taken as 10 theta. When the angle is small, can be taken as theta. This is 2 up to 15 degree. So this will give me theta by 2 is equal to dr over 2r, or theta b is equal to dr over r. And theta b is also equal to lambda by dt. So this theta b is approximately equal to dr by r, and theta b is equal to lambda by dt. So I can convert this solid angle omega b using this formula, 2 pi 1 by cos theta b by 2, and this expression gives pi by 4 theta b square, because what you can do is, if I write this equation, this is 2 pi into 1 minus cos theta b by 2 is actually 2 pi 1 minus, I can write in this fashion, sine square theta b by 2 raised to power half. So this will be 2 pi into 1 minus, and this theta b is very small, so this can be written as 1 minus half. This half can come here, sine square theta b by 2. So this will give me 2 pi. This 1 and minus 1 will get cancelled, and what you get is half sine square theta by b by 2. Again, I invoke the same thing, that theta b is small, so this will become 1 by 2 pi by 2 pi into theta b over 2 whole square. Sin theta is equal to theta, and theta b is small. So if you do this, what you get is 2 pi into theta b square over 8, which is nothing but theta b square pi divided by 4, pi by 4 theta b square. So let us write it cleanly here. This is pi by 4 theta b square. So this is what I have written here, pi by 4 theta b square. And let us define the GT as that 4 pi, the whole solid angle divided by this solid angle, omega b, and putting these values of theta b and using these expressions, what I get is GT is equal to 4 dt by lambda square. This is a transmit gain. So this is an expression for transmit gain. This also you can, because we know that theta divergence is equal to lambda by dt is 1.22 lambda by dt, but for approximation we can take lambda by dt, and if I put this dt in this expression, this can also be written as 16 over theta divergence whole square. So this is another equivalent expression for gain. If theta divergence is given, you can calculate straight away, you can calculate the transmit gain. And if transmit aperture is given, then you have to put the value of dt here and then get the value of the transmitter gain. So this is the transmitter gain. Transmitter gain. And if I calculate the optical intensity, which is power divided by area. So I get, this is the gain part, and this is the transmit power divided by 4 pi r square gives the optical intensity. So this is expression for I optical intensity, which is GT into PT divided by 4 pi r square. So PR power, the receipt power, now it is falling on some area of the detector. This is area of the detector or area of the receiving device, area of the detector. So GT PT divided by 4 pi square is the transmit part. GT is the transmitter gain. PT is the transmit power divided by the 4 pi r square. And this falls onto the area of detector. So that basically it will be GT PT 4 pi r square into A. And the GR, the gain at the receiver, can be written as 4 pi by lambda square, that area of the detector. So from here you can get A, which is lambda square GR 4 pi. And if you write now the complete equation, which has GT transmitter gain and the GR, the receiver gain, and the space loss. This is the space loss part, because the light will lose its intensity as it travels. So this is because of the space loss. So this is the receipt power you get at the receiver. This, let me again write here, this is transmitter gain because of the optics of the, which I am using as the transmitter. This is a transmit power. This whole thing is space loss, which is given by lambda by 4 pi r. R is range equation. And GR is the receiver gain. Again, using some optics at the receiver. So GR is the receiver gain. So in order to make this complete, I need to consider other factors also. For example, I'm using some optics, there may be some loss. So this is loss due to transmit optics, loss due to transmit optics or transmitter optics. This is the pointing loss, because the transmitter and receiver, if they are not aligned or if there is some mismatch, there will be some loss of power. So I need to factor in this also, which is called as pointing loss, pointing loss. And then this is the space part, which is taken from here. GR is the receiver gain. And then you have the NR, this is the loss due to receiver optics, loss due to receiver optics or at the receiver. And this loss could be because of the filter, optical filter, which you might be using in the receiver. So optical filter loss or gain depending upon what it does, right? So the complete expression is PR is equal to PT into GT, neta T into neta PL, pointing loss, space loss, lambda by 4 pi R whole square. GR is a receiver gain, and loss due to receiver optics, neta R, and neta lambda is because of the filter, loss because of the optical filter. Now let us try to understand this receipt power. How idea is to increase this receipt power. Because more the receive power, then I'll be able to decode the signal correctly. I'll get higher data rate. So idea is to increase the receipt power. Now for increasing the receipt power, this PR, I can either increase PT, but increasing PT, I cannot go beyond a certain limit because issues related to eye safety, for example, because it is outdoor, where you may have some human beings, right? So eye safety requirement one has to meet. Then there will be some thermal issues, because high power means you require a source which generates high power, you require large kind of current which will produce heat. So there are thermal issues there. So these are the constraints. I mean, you can't go on increasing PT in order to get high PR. So one has to work under these limits of eye safety and thermal management. The other option is I increase GT. As we know, this GT is equal to 4 dt divided by lambda whole square, or this is also equal to 16 theta div whole square. So if I want to increase GT, that means I have to decrease theta divergence. Theta divergence meaning I have to make the beam very, very narrow. If I make the beam very, very narrow, and there's a receiver here, this alignment becomes very, very critical. Even if there is a mismatch of the alignment, you will not get any signal. So there is a limit up to which I can, decrease theta divergence. So lower value of theta divergence means I require strict alignment, which may not be possible in practice. So again, one has to do within a certain limit. These anyway, you have to keep small. The losses which are happening because of the optics, one has to keep very, very small. Pointing loss is also has to be kept low. And sometime you have tracking mechanism so that this pointing loss is kept minimum. So whenever it goes, it misaligns, there is some feedback mechanism, and then there is alignment is established. So you can reduce this pointing loss. Space loss, it is, depending upon the distance, you can't do much about it. Then you have the GR, and we know the GR is actually 4 pi by lambda square into area of the detector, or the area of the receiving device. Area of the detector or area of the receiving device. Now I want to increase GR, means I have to increase this area. The moment I increase the area of the receiving device, first of all, increasing the detector area will give you high capacitance. Then it may not respond to high data rate because the capacitance is high. And also if I increase the area, you will have more background noise coming to it. So your signal to noise ratio will go down. So again, there is a limit to which you can increase your area if you want to increase PR. And similarly, one has to use optics, which has less loss at the receiver. And then same logic is for filter which are using, you should have minimum loss. So you see here the trade-off. In order to get high PR, I can play with different components, but every component has some limit, or every parameter has some limit. So this is how it becomes a design problem. Okay. So let us do one example just to understand, what kind of values we get. So suppose I have a source at say 500 nanometers. This is a wavelength I've selected. This is an arbitrary wavelength I've selected. And distance is, say, for example, 350 kilometer, and I want to calculate, theta divergence and the receive aperture. So my beam will become something like this. So this is a dr, and this is a theta divergence. And dt I use here is, let me show here, dt, or the transmit aperture length I've used has dimension 4.7 centimeter. And this length is 350 kilometer. So I want to know what is theta divergence required and what is the dr I will get. So theta divergence, here I'm using exact formula 1.22 into lambda by dt. Earlier I have been using lambda by dt, but just to get some feel of the values, I have used 1.22 lambda by dt. Just putting these values, what you get is 1.3 into 10 raised to minus 5 radian. So it is in micro radian, 0.13 micro radians. And this dr, this is dr by 2 and theta div by 2. So you can write dr is equal to 2 theta L. Actually, this is divergence into L is 350 kilometer. And so what you get here is a 9.1 meter area of beam width, beam spot. So just to give you some ideas about this. So if you want to get less dr, for example, you have to decrease theta divergence. For decreasing theta divergence, you have to increase the dt. So this is all trade-off here.